Alright everybody, welcome to our third video on section 612, integrating using partial fractions. This is actually an extension. We're going to talk about advanced partial fraction problems that you will definitely not see on your AP exam. As we note here, you're not responsible for this material. So there are two types of problems that we'll run into here. The first is when we have a repeating linear factor, and the second is where we have an irreducible nonlinear factor. So let's go right ahead and we will start with the first situation. A repeating linear factor. If when we factor the denominator, multiple occurrences of the same linear factor occur, then in our partial fraction decomposition, we need to use every power of the repeating linear factor, starting at the first power and going up to however many times the linear factor repeats in the factorization. For instance, x squared minus 4x plus 4 is our denominator here. That factors as the quantity x minus 2 quantity squared. We can't just make it a over x minus 2 and b over x minus 2 because that's the same denominator. So what we do is we have a over x minus 2 and b over x minus 2 the quantity squared. And that's how we're going to break this particular partial fraction problem down. And so, when we try and find the values of a and b by setting up our system of equations, we want 4x minus 3 to be equal to whatever these fractions are, whatever these numerators are, when the denominator is x squared minus 4x plus 4. So we need to multiply this one by x minus 2, and then for the second denominator, we don't need to multiply it by anything because we already have x squared minus 4x plus 4 as our denominator. So this is just b. And so our system here, we've got ax minus 2a plus b is equal to 4x minus 3. And so our system is going to be a equals 4 and negative 2a plus b equals negative 3. And we can solve this and we find that b is equal to 5. And so this is our integral that we're going to be taking. We're going to have the integral of 4 over x minus 2 plus 5 over the quantity x minus 2 quantity squared. And there's our integral. We're going to go ahead and take the antiderivatives. That's 4 natural log of the absolute value of x minus 2. But now since this one's to the second power, instead of being a natural log, we're just going to use the power rule in reverse. And there's our integral. All right, let's look at situation number 2. Here we again have a repeating linear factor. And what happens here, since we've got another factor, when we decompose this, we want the other factor to have its own denominator. And then we're going to have two more fractions, one with x plus 2 to the first, and one with x plus 2 to the second. All right. And now we need to figure out what our system of equations is going to be. And so in order to get our common denominator, this first one needs to be multiplied by the quantity x plus 2 quantity squared. So that's a times x squared plus 4x plus 4. The second fraction here needs to be multiplied by x minus 3 and by x plus 2. So that's x squared minus x minus 6. That gets multiplied by. And then my last one only gets multiplied by the quantity x minus 3 to get our common denominator. And so now we're going to set up our system of equations. We've got ax squared. Ooh, what the heck? A little technical glitch there. I think I fixed it. We've got ax squared plus bx squared. There's no x squared with the c. That's equal to the 5x squared. So a plus b equals 5. X's, I've got 4ax minus bx plus cx. That's equal to the 6x. And then my numbers, I've got 4a minus 6b minus 3c is equal to 12. Okay, now, of my three equations in my system with three variables, the first equation has no c, so I'm going to combine the other two to get rid of the c's. So I'm going to multiply this equation by 3. Gives me 12a minus 3b plus 3c equals 18. Which gives me 16a minus 9b equals 30. And then I'm going to go ahead and combine that with this first equation. I'm just going to multiply the first equation by 9. Gives me 9a plus 9b equals 45. Which leads me to 25a equals 75. So, a equals 3. Substituting back in here, we get b equals 2. And substituting back into any of the other equations, let's see, we've got 12 minus 12. We get c equals negative 4, it looks like. Let me just quick check that. That's 12 minus 12. Okay, that works in there. And 12 minus 2. Yep. All right. So now we can go ahead and write our integrand with our constant values. And we've got 3 over x minus 3, and 2 over x plus 2, and negative 4. Well, let me just make that a minus 4 instead of making it plus a negative 4. Minus 4 over the quantity x plus 2, the quantity squared. And now we integrate term by term. We've got 3 natural log of the absolute value of x minus 3, plus 2 natural log of the absolute value x plus 2, plus 4 over the quantity x plus 2. Power rule in reverse. And there's our integral. All right, so that's what happens if we have a repeating linear factor. The other possibility is that we have an irreducible nonlinear factor. So if when we factor the denominator, a factor appears that's larger than linear and can't be broken down further, which we'll see in this first example, we need to modify what we do with the numerator. Normally we just put a constant in the numerator, but instead of just having a constant, what we need is we need an expression that's 1 power lower than the irreducible factor. So if we factor and we get an irreducible quadratic, our numerator will need to be ax plus b. If we had an irreducible cubic, we would need the numerator to be ax squared plus bx plus c, etc. So let's see what happens here in my factorization. I've got 4 terms. I can take an x squared out of those. That's multiplied by x. That's multiplied by minus 3. That's plus 4. And so my factorization is the quantity x minus 3 times the quantity x squared plus 4. And x squared plus 4 is an irreducible quadratic. We can't factor that any further. So we have exactly the situation that we're talking about here. So this is going to be equal to a over the quantity x minus 3 plus bx plus c over the quantity x squared plus 4. Because we need the numerator to be linear over that quadratic denominator. And now we're going to multiply in order to get our system of equations. We need to match this numerator. In order to get that, we're going to take the numerator of this times this denominator plus the numerator of this times this denominator. And so we're going to actually have to multiply those out. It's ax squared plus 4a plus bx squared minus 3bx plus cx minus 3c. And now we're going to write our system of equations. I find my x squareds, and that gives me one equation, a plus b equals 9. I do my x's next. And so I've got negative 3b plus c equals negative 7. and then I do my numbers. 4a minus 3c equals 18. So now what we have is we have a system of equations in 3 variables, but each of the equations is missing one of the variables, and a different one in each case. So what I'm going to do is I'm going to combine 2 of these equations to eliminate the missing variable from the other one. So I'm going to leave this equation alone, the a plus b equals 9, and I'm going to combine these bottom 2 equations to eliminate the c. So I'll multiply this by 3, gives me negative 9b plus 3c equals negative 21. And then when I add these 2 equations together, I get 4a minus 9b equals negative 3. Okay, notice we eliminated the c, but we added another variable into both of those equations. All right, and then we will multiply this top equation by 9. Gives us 9a plus 9b equals 81. And we get 13a equals 78. So a equals 6. Since a plus b equals 9, that means b equals 3. And c is going to be, let's see, if a is 6, that's 24. So c's got to be 2. All right, so now I set up my integral. This becomes the integral of 6 over x minus 3 plus 3x plus 2 over x squared plus 4. And usually what we have to do in one of these problems is we're going to have to split this into 2 integrals. So we'll turn this into 6 over x minus 3 plus 3x over x squared plus 4 plus 2 over x squared plus 4. Okay, so this is going to be 6 natural log of the absolute value of x minus 3. This one, I'm going to use a substitution. So I'm going to use u equals x squared plus 4. So du is equal to 2x dx, which makes this the integral of 3 halves. I should put that 3 halves out in front. Plus 3 halves the integral of du over u. Okay, and this one's going to be an arctangent substitution. We want to replace x squared with, let's replace it with 4t squared. So x is equal to 2t, so t is equal to 1/2 x. So dx is equal to 2 dt. This becomes the integral of 2 dt, 4 dt, because I already have a 2 there. 4 dt over 4t squared plus 4. And I can integrate this first one. That's a natural log of the absolute value of u. And for this one, I can factor a 4 out of the numerator and a 4 out of the denominator. 4 over 4 is 1, and so this turns into this integral. That's the arctangent of t. And now I just need to bring my substitutions back. U is x squared plus 4, which is always positive, so I don't need the absolute value. And t is 1/2 x. And boom, there is our integral of our original problem, which was polynomial over polynomial. All right, that brings us to the end of this video and the end of this lesson and the end of our discussion of partial fractions. So come on back for our next section, section 6.13, which is the last BC exclusive section of Unit 6. All right, see you folks again in the future. Have a great rest of your day. Bye.